Hi, thanks for coming on this beautiful evening. You're not sacrificing so much, though, because it's a beautiful setting here, isn't it? The title of my talk is Anticipating a New Golden Age. In the 20th century, in fundamental physics, we had, I think it's fair to say in retrospect, 3 golden ages. We had a golden age around the year 1910, when the theory of relativity developed. Another around 1925, with the development of quantum mechanics. And another around 1970, with the development of the core theory, what's usually called the standard model, to make a truly great achievement seem boring. That's, to this day, our powerful, accurate, complete understanding of normal matter on a fundamental basis. I think we're poised for a new golden age, the first one of the 21st century. We have beautiful ideas that have been ripening and maturing for the last 20 years. And they've only come to look better and better as we study them closer. And as the data supporting our core theory has solidified. Now it's time to consult nature and see if these ideas are really nature's ideas, if she thinks they're beautiful too. And finally, now we're going to have the tool at hand that will make it possible to dialogue with nature on this subject. It's called the Large Hadron Collider, or LHC. If you fly over Geneva and look down, you see this kind of scene. The Jura Mountains in the background, it's kind of mystical. This is Lake Geneva. Geneva is over here. And then you see something really surprising. You see this gigantic red ring. 27 kilometers, or about 18 miles around. That's the LHC. In many ways, it's our civilization's answer to the pyramids of Egypt. It's on that kind of scale and involved that kind of effort. But it's much better, I'd argue, because it's a monument to curiosity rather than superstition, and is based on cooperation rather than command. Now, of course, I was joking. You don't really see that if you look down from an airplane over Geneva. Almost all of it is underground. So this is a more realistic portrayal of what you see, namely nothing, a few little things. But underground is that big ring. This is a rather abstract picture. Here's what's in the ring. These are superconducting magnets, similar to the magnets that you would use in magnetic resonance imaging for medicine, but more powerful. They have to be kept at 3 degrees Kelvin, so they stay superconducting. These go around for 27 kilometers. They're machined to within microns, so that they can guide protons around this ring. The protons have to go on precise paths. They will be moving within a part in a billion of the speed of light, the limiting velocity, so they have extraordinary energy. At a few points, the beams will cross and protons will collide. In those collisions, we reproduce conditions last seen within a microsecond of the Big Bang, that kind of energy and density, although not in the whole universe, just in a very, very small volume for a very short time. And we want to understand what comes out of these little bangs. This is the kind of detector. This is the scale of one of the detectors, the so-called Atlas detector. To see what it is on a human scale, to see that this is a railing for people. It's 10 stories high, but it's also 10 stories in the other two directions. That's the civil engineering. The logistics of constructing it was mind-boggling. But more important than the size, and more impressive than just the size, is the complexity and precision of what goes into it. So here's a side view that gives you some idea of when that scaffolding is being filled with detectors. This is precise, state-of-the-art, fast electronics so that you can follow particle tracks. A million collisions roughly per second occur. They all have to be sorted out. Out of these collisions, out of the fireballs come many particles moving at close to the speed of light. You have to sort them out. I'll show you. Well, this is sort of what an event looks like. You have to sort it all out and find the patterns. It's even more densely instrumented in the core. I just like showing these pretty pictures. It's really inspiring. And again, you can see here are the humans to set the scale. And so that the collisions will actually occur in there. That's what the picture that emerges from this detector. So all this electronics fires so that you can follow the very rapid paths and sort them out with very fine resolution of the particles that emerge. The information that we really want is highly encoded. That picture may have looked like a mess to you. Well, it is kind of a mess. The messages that we try to extract from it are highly encoded. To get them out requires enormous amounts of computer processing. So there's a hierarchy called 3 levels of triggering. Each level has something like this, where you sort out the events one by one, throw away most of them because they're due to physics we understand. We're not interested in just confirming what we already know. So eventually, about 1 in a trillion events gets to the last level, and a human being looks at it and tries to figure out what it means. So, I hope I've given you a sense of the scale and the ingenuity of this effort. But that's just mechanics. What is it actually trying to do? Well, it's really, in a way, very concrete and mundane. It's very much in the tradition of Van Leeuwenhoek and his microscope, which first allowed people to see cells, or Rosalind Franklin's X-ray pictures of DNA, which enabled people to see the atomic structure of DNA. Those pictures use respectively light for Leeuwenhoek and X-rays for Rosalind Franklin. X-rays can look at smaller distances than light. We want to look at much, much smaller distances. And so it requires a different kind of instrument. In fact, it requires the kind of instrument that I described, this LHC. What it is no more and no less than a microscope whose resolution is about 1 billion times better than X-rays. And because the interesting action there occurs on time scales is very fast, it also has to be something that resolves very swift times. So it's an ultrastroboscopic nanomicroscope. And what it does, what is it taking pictures of? It takes pictures of empty space. Because in modern physics we learn that that's really where the action is. The primary object of our theories is space-filling material, a space-filling thing that doesn't have a standard name, so I made one up. I call it the grid, out of which the particles we observe that we're made out of emerge as kind of secondary epiphenomena, little ripples on the grid. The grid is full of spontaneous activity and potency, and it's the primary object of reality. It fills all space. And that's what we're studying. Empty space, that is what appears as empty space to us, has it all. Everything that exists in reality, according to basic principles of quantum mechanics, that can possibly exist, can possibly be created, gets created spontaneously in what's called virtual form, which means in a form where it only percolates into reality for a very short time and then fades back into empty space. So empty space has this foam, if you like, of virtual particles which come to be and pass away without getting very far, either in space and time. And that's the kind of structure we're trying to resolve. We can already do that using the reliable equations and experimental results of the core theory to a certain extent. Our eyes were not evolved or created to resolve distances as small as 10 to the minus 14th centimeters or times as small as 10 to the minus 24 seconds. Having that kind of perception wouldn't be useful in avoiding predators or finding desirable mates, the kind of things that contribute to our fitness that we were evolved for. But now, using our noodles and analyzing the results of our equations and experiments, we can reconstruct what our eyes would see if they were capable of such resolution. And here it comes. This is the deep structure of reality. This is an actual numerical simulation of fluctuations in the energy in gluon fields. These are equations that have many consequences we can check and have checked, so there's no doubt that this is what empty space would look like if you could see with those kinds of fine resolutions. So here it comes, the deep structure of reality. Can we take down the lights a little bit? This is what it looks like. You see, it's a lava lamp. But this is an honest-to-goodness numerical calculation of fluctuations. It's simplified in a little ways. I smoothed it out. So this is due to Derek Lineweber from Australia. It's smoothed out so you make a nice movie out of it that's not too jagged. It looks continuous, even though there are only 5 frames. Of course, in reality, there are not just 5 frames. It doesn't repeat itself, and this is only a small volume. But you have to imagine that everywhere in space and time, all the time, everywhere and every when, this is happening. And we want to see what's happening at even smaller distances and faster times. That's the name of the game. In the quantum world, to see something, you have to disturb it. Okay. There's an irreducible disturbance in a system if you want to observe its properties. This is related to Heisenberg's uncertainty principle. If you want to know where a particle is, you have to have uncertainty in its momentum. So if you want to measure where a particle is, you have to kick it so it can have some uncertainty in momentum. So that's probably familiar to many of you. In the deep quantum world, I'm going to go one level down, it's more drastic. To see something, you not only have to disturb it, but in many cases you have to create it. So to see, for instance, the fluctuations in empty space, due to a heavy particle, which are of very short duration and very localized, you have to supply enough energy to make that particle. That's why we don't see those gluon fluctuations all the time. We don't supply enough energy to actually create them and sort of bring them out of the equations and into life. In deep quantum mechanics, to see these things, you not only have to interact with them, you actually have to create them. And this is another way of looking at why the LHC is what it is, another aspect of it, a dual aspect in the sense of quantum duality. To produce a particle, a new particle that has a heavy mass m, you have to supply at least the energy that's the smallest energy that particle can have, because total energy is conserved. So if you have a particle of mass m at rest, its energy is mc squared, according to Einstein. That's the very least amount of energy you need to produce a particle of that type. That's why looking at short distances and producing new kinds of particles is called high energy physics and involves these gigantic accelerators. Okay, so now you've understood the physics of LHC quite a bit, and we're ready to wrap.
27 kilometers tunnel underground, designed with mind that sends protons around a circle that passes through Switzerland and France. 60 nations contribute to scientific advance. Trillions of protons swing round through the ring they ride, till in the hearts of the detectors that makes it collide, and all that energy packed in such a tiny bit of it becomes mass particles created from the vacuum, and then.
Oh yeah.
So
LHC is where the antimatter's gone. Alice looks at collision with a red ion. CMS and Atlas are two of a kind. They're looking
these
for
are the
whatever
different
new particles they can find. The LHC accelerates the protons in the lead and the things that it is.
You can get up and dance
When
if
the
you
head,
like.
we see Atlas and planet. Stars galore, we know a black hole resides in each galaxy's core. But even though that matter cannot explain what holds all these stars together, something else remains. The star matter interacts only through gravity. And until you catch a particle, there's no way to see. Take it back to conservation of energy, and the particles appear as clear as can be. You see particles flying in jets they spray, but you notice there ain't nothing going the other way. You say my law has just been violated. That don't make sense. There's gotta be another particle to make this balance, and it might be dark matter. And for the first time, we can.
This has a lot of good physics in it.
So
I hope. This is all on site with real scientists.
Because when it meets its normal twin, they both annihilate. Matter gives the energy and then it dissipates. The matter is created from energy, which is exactly what they'll do in the LHC. You get matter and antimatter in equal parts, and they try to take this back to when the universe starts, the Big Bang. Back when all the matter exploded, but the amount of antimatter was somehow eroded. Because when we look around, we see that matter abounds, but the antimatter's nowhere to be found. That's why. Antimatter's gone. Alice looks at collisions of lead ions. CMS and Atlas are two of a kind. We're looking for whatever new particles they can find. The LHC accelerates the protons in the lead, and the things that it discovers will rock you in the head and leave spell. That's the one that everybody talks about. And there's the one sure thing that this machine will sort out. If it Higgs exists, they ought to see it right away. And if it doesn't, the scientists will finally say.
Not quite right, by the way.
Something interesting about when I'm right with the Higgs. I still haven't said just what it does. Let's suppose the particles are mass because there is this Higgs field that extends to all space. As the particles slow down while other particles race straight through like the photon. It has no mass, it's something heavy like the top or the X dragons. And the Higgs is the photon that carries the force. And the particles take orders from the field that is its source. They'll protect it. What actually means is when the antimatter's gone, Alice looks at collisions with the lead ion.
We're almost done. In fact, the rest of it is mostly wrong.
You see, gravity is weaker than we, and the reason why is something many scientists see. They think about dimensions, clearer than just three. But maybe there are others that are too small to see. It's into these dimensions heavy expense. Takes to seem weaker here on our end. At least the punches are rolled up, feel so tight, but they don't affect you in your day-to-day life. But if you were as tiny as a graviton, you could enter these dimensions and go wandering on, and they find you. HPBs, these are the animators on. Alice looks at collisions of lead and ion. CMS and Atlas are two of a kind. They're looking for whatever new particles they can find. The MHD accelerates the photons in the lead, and the things that it discovers will rock you in the head.
Oh, yeah. Our understanding of the universe is about to
Okay.
change. Thanks to the large
You. Now, I'd like to present my vision for what I hope, expect, and have worked on, pioneered, championed for years will happen at this machine in terms of advancing our fundamental understanding. In this core theory that I mentioned, also called the Standard Model, there are 4 different interactions. There's the strong force, the weak force, which act most importantly in the subnuclear world. And then there are the classic forces of electromagnetism and gravity. Let's leave gravity to the side for the moment. The other 3 forces obey equations that have a family resemblance. They they have a family resemblance. They're deeply similar in their mathematical structure. So we'd like to think that they're part of one happy family, one unified field theory. And when you try to implement that idea, a lot of things work. Equations which seemed lopsided and arbitrary within the core theory itself, from this new perspective, are lopsided in just the way they have to be to fill out the family tree, so to speak. But one thing doesn't work, or at least doesn't seem to work at first sight. That is that if we're going to regard all these different forces, these 3 different forces, as aspects of one more basic force, all on the same footing and all symmetrical with each other, then they should have the same power. That is, the same strength. But the strong force really is stronger than the other forces. And so if we plot strength of interaction going down, it's on the bottom. And the weak and electromagnetic have different strengths. But remember the lava lamp. When we look at the properties of particles and how they interact, we don't see necessarily the most basic primeval qualities they have. We see them through this medium, which introduces kinds of distortions. It's as if we're fish looking through an ocean that distorts our vision of things. And so we have to correct for the effect of all these distortions. If we want to go down to short distances where the basics are and see if things get unified down there. And this is very much beyond our powers to do directly experimentally or very far. But we have the equations. In fact, they're these equations of asymptotic freedom that Ellis mentioned, that enable us to calculate the distortions and make corrections and see what happens if we strip away the distortions and get back to the fields or the particles in themselves. And this is what we calculate. If you take the appearances over here and strip away the distortions, by golly, they do unify. They do seem to be different aspects of one underlying primeval reality. Unfortunately, or fortunately, there's a caveat, an asterisk here, which is that in this calculation, we have to correct for everything. These fluctuations. I said everything fluctuates in quantum theory. So we get fluctuations due to everything that exists. So we have to know what exists. We have to, and this calculation, the successful calculation, is assuming not only that the different interactions appear on the same footing, or that's really what we're testing, but also assuming that the different kinds of matter and light, if you like, more specifically, fermions versus bosons, that is, electrons on the one hand and photons on the other, can be seen as part of one underlying symmetric reality. This is an idea called supersymmetry. It also involves expanding the equations of physics, and necessarily involves, because we expand the equations, the existence of new phenomena, new kinds of particles. On the good side, that's just what we need when they appear as corrections to make the unification really work. On the potentially bad side, but also potentially very exciting side, those particles had better exist as real entities. So the unification only works if we expand our model of the world to include another unifying idea, supersymmetry. That brings in new fluctuations, new corrections, and new particles which must be produced at the LHC. Here's a more formal version of the plot of the different couplings coming together with numbers. I won't go into it. But I want to build on this one to emphasize something I swept under the rug before. I said, let's ignore gravity for the moment. What about gravity? How does gravity fit into this picture, the fourth fundamental force? Well, at first sight, it looks absolutely absurd. Here, where we actually measure things at these relatively low energies, as a force between elementary particles, gravity is ridiculously weaker, feebler than the other forces. You see, these guys differ by about a factor of 10 in their underlying strength. Gravity, if you compared them at atomic distances or macroscopic distances, they're both 1/r² forces, so it doesn't matter so much where you compare them at those large distances. You would find that gravity is weaker by a factor of 10 to the 40th. So 1 followed by 40 zeros. So not just 1 power of 10 that takes you from here to here, but another power of 10, so 10 times as big, and then 10 times as big as that, and 10 times as big as that, 40 times. So gravity would be way outside the known universe. Looks ridiculously weaker, just absurdly weaker than the other forces. And that's probably the most difficult thing to understand about gravity. But we've learned that the basics occur at a very much shorter distance, and we have to calculate what gravity is doing down there. Well, we've done the calculation, and here it comes. So from way outside the known universe, remember this is inverse coupling, so this very weak gravitational force is way up high. From way outside the known universe, here comes gravity. At the last second, unifies too, more or less. So it's a very tantalizing picture. There seems to be a grand synthesis of all the different interactions emerging, not as something vague, but as a very precise numerical synthesis or unification of all the different couplings. So nature is singing for us a siren song, saying that we should bring things together. When we succumb to that temptation to unify things, we get rewarded. Things really do work that didn't have to work. Is she teaching us or teasing us? So there's Mother Nature. And here I am, in my youth, being tempted by this siren. There's a trial by fire now. That machine, the LHC that I described, is going to be the trial by fire for these ideas. We wanted these particles in their virtual form to make the unification. They also have to exist when we supply enough energy in their real form, and that's what the LHC will be doing. So it's a trial by fire. Maybe they won't show up, and all this will go up in smoke. Or maybe here I am. Here I am. We'll start to see emerging from these very complicated analyses and detectors evidence. Not for a new particle. I mean, yes, it is a new particle, but that's not the point. It's evidence that we can achieve a much more unified, beautiful, and coherent account of the basic laws of nature. So, we'll see. It's an exciting time to be a physicist. I hope I've convinced you. But more than that, you don't have to be a physicist to appreciate these things. You can expand your mind by learning about them and appreciating the stakes, what's involved. It's really an exciting time for all thinking beings. Thank you very much.